Hi everyone, we are Team 5507, the Robotic Eagles from George Washington High School in San Francisco, California. My name is Leah.
And my name is William, and we will be your two presenters for this presentation. Um, this season, our team worked entirely remotely as our school did not allow us to meet in person, but we still tried our best to complete all of the challenges. For a quick presentation overview, today we'll first go over the robot and some team goals that we have, then the design and build process, and lastly, some engineering features on our robot. So first, what is our robot designed to do? Our robot, Daphne, was designed to tackle all aspects of the 2019 to 2020 Infant Recharge game.
Our team's goal is to be an alliance captain, meaning we need to finish in the top 10 of the regional that we attend. To meet this goal, we need to have fast cycle times, which means we need to be consistent. And to be consistent, we needed high accuracy when shooting, quick intake when picking up power cells, and dynamic motion driving. We also needed to have a climber that is reliable, fast, and stable so that it can balance. This is our four-step design process that we follow each year, but we're going to focus more on the manufacturing and iterations phase. Throughout the construction of the period of the robot, we build multiple iterations of the initial design, each building off of the robot's previous version's strengths and weaknesses. We want to first get something working and then improve the mechanisms later to a satisfactory point.
Next, we're going to go over some engineering features. So first, some autonomous features. Originally, Daphne was programmed to have a 15-second two-cycle autonomous route for the 2019 to 2020 Infinite Recharge game, but currently Daphne has code for the AutoNav challenge to automatically follow a path. Now, we use NavX sensors to help determine the rotational position of the robot and encoders to help determine the linear position of the robot based on how many times the wheels have rotated. We also employ a limelight vision camera to automatically align Daphne when shooting and help sense power cells. And we also have a time of flight sensor, which controls the conveyor and is also used during the Galactic Search Challenge to help determine which path we're following. Next, we have the climber. The climber is built with two arms, each on the opposite side of the robot, which are designed to neatly fold down to be compact and allow Daphne to fit underneath the control panel. The lower section of this climber is actuated by a rack and pinion, and the upper section uses a spring. This climber is very efficient in that it's easy to hook onto the shield generator, first by extending the arms, then driving forward until the sensors detect the bar, and lastly retracting the arms to pull Daphne into the air. The climber also has a lock mechanism to keep the robot aloft, and this locking mechanism is built with a pneumatic cylinder with the locking gear attached at the end, which slides up the rack to lock the climber. It uses 3 gears to lock, one from the rack, the pinion, and the locking gear, and is used when the round is over and Daphne is hanging on the shield generator, but still disabled, and it's used to keep Daphne from falling to the ground. And the reason this locking mechanism works is that 3 gears can't spin at the same time because gears work by rotating in opposite directions. And with 3 gears, the third gear will just jam the first 2.
Our robot's conveyor best highlights our engineering process. We originally had a single-sided conveyor, but quickly realized the conveyor jammed, so we switched to a double-sided conveyor. We also installed a time-of-flight sensor to drive the conveyor a certain distance upon detection of a power cell, to be able to fit 5 cells inside without jamming the mechanism. For our first prototype, originally the lower conveyor only had one belt on one side, which resulted in friction between power cells causing jams. Secondly, we added a second sag to the conveyor belt at the bottom for a double-sided opposite rotation, but ran out of motor control panels on the power distribution panel. To get around this, we tried adding a figure-8 polycord, but it constantly slipped and didn't spin both sides reliably. Lastly, our final solution was a custom gearbox that we designed in order to drive both sets of belt with one motor. The custom gearbox is located on the back of the robot. It drives both sides of the conveyor belt so they spin in opposite directions at the same speed, making the power cells move in one direction. Our custom gearbox is powered by a Neo motor with a 16-to-1 gearbox, making it powerful enough to power through jams.
Our robot's drivetrain is a Swerve drive. This allows us to both move linearly and rotate at the same time. Our Swerve drive also has custom software for kinematics and odometry. Our shooter was designed to shoot from the target zone, limiting opposing defense and guaranteeing 100% accuracy. It has a flywheel to increase angular momentum to moderate the fluctuations in spinning speed, and has two Falcon 500 motors, each on the opposite side of the shooter. The shooter creates backspin when a power cell is launched. This backspin keeps power cells from bouncing out of the outer goal and back onto the field. And as I stated before, the shooter also has a limelight vision camera attached, allowing for automatic alignment.
The intake is built with vector intake wheels to center the power cells as they enter the conveyor. It also uses a pneumatic cylinder to fold up the intake bar to be more compact. The control panel spinner is a retachable spinner module, meaning it can extend up to reach the control panel. The spinner is compliant, compact, and has a built-in color sensor with code to center the control panel. We employ a rigorous goal-based design process to maximize the efficiency of our final product. Our robot Daphne has a resilient and reliable climber, a double-sided conveyor with little to no jamming with maximum storage, a swerve drive to allow optimum movement, a control panel spinner, a quick intake system, and an efficient, reliable shooter. This concludes our presentation. Thank you so much for listening.